You have seen last time in linear algebra course, linear transformations. Now, here we will see introduction to the important concepts of linear algebra like eigenvalues and eigenvectors. Hello, I am Professor Y.M. Borse from Department of Mathematics, Savitribai Phule, Pune University. So, in linear algebra, matrices are used to represent linear transformations. Yes. So why you learn matrices extensively in linear algebra? Because they represent linear transformations. A natural question arises. Are there vectors whose direction remains unchanged under a linear transformation? For example, if you take rotation, which is a linear transformation, then you can see that every line shifts. If you take reflection along x-axis, it is a linear map, and x-axis remain fixed, right? So there is a possibility that something get fixed. So we have a general question that if you operate linear operator, say t, on a vector x, with what happens to x, right? Whether it remains unchanged or it changes. So such a special vector are called eigenvectors. If a vector changes, means it only shifts its position on the line passing through that vector and zero, then we call it the eigenvector. And how much the scaling factor in which the vector is shifted along the line is called eigenvalue. So this is roughly. So let us see the uh, proper definition. So as said earlier, matrix represents linear transformation. Therefore, we defined um, eigenvalues and eigenvectors of a matrix. Let A be a square matrix of order n, which it is n by n matrix. A non-zero vector x in Rn is called eigenvector if Ax equal to lambda x for some scalar lambda. So we call lambda as eigenvalue and x as corresponding eigenvector. So A operates on x, then x changes to lambda x. So A only stretches or shrinks x without changing its direction. A only shifts x to lambda x, where lambda is a scalar. So magnitude changes, but direction remains same. So for Ax equal to lambda x, so if you want to find out lambda and x, how we can do it? So suppose Ax equal to lambda x, then A minus lambda I x equal to 0. It is a matrix equation. And since x is not 0, so the determinant of A minus lambda I equal to 0. And this equation, if you work out, it is a equation in lambda of degree n, and we call it as a characteristic equation. And if you find out the roots are called characteristic values or eigenvalues of A. Again, substituting values of lambda in the first equation, A minus lambda x equal to 0, and if you solve the system of equation, we get the eigenvector. Let us see the illustration. Consider this 2 by 2 matrix 2, 0, 0, 3, and work out the determinant of A minus lambda I. Then what you get, 2 minus lambda, 3 minus lambda, and the roots are 2 and 3. So eigenvalues are 2 and 3. If you work out, you can see that the eigenvectors are 1 0 and 0 1. Okay, so you can see that how you can find eigenvalues and eigenvectors by the calculation. Now we just see why eigenvalues and eigenvectors are important. See, they can simplify matrices via a process called diagonalization. You know, if diagonal matrices are easy to handle, uh, eigenvalues reveal intrinsic properties of linear transformations. They indicate whether a system is stable, unstable, or neutral over the time. There is an important application called principal component analysis. Eigenvectors give principal directions, while eigenvalues measure data variance in a large data. Also, they are used in graph theory and networks. Eigenvalues reveal connectivity and structural properties of graphs. Okay, I stop here. In next lecture, we will see in detail applications as well as more problems. Thank you. Thank you very much.